Alright folks, let's talk about something super fundamental to your PC, your phone, pretty much any smart device you own. I'm talking about interrupts. Think of an interrupt like a super important, attention-grabbing doorbell for your computer's processor, its CPU. When this doorbell rings, the CPU knows it needs to drop what it's doing, at least for a moment, because something else needs its immediate attention. It's a signal, a poke, a hey, look over here. Message that can come from all sorts of places, both inside and outside your computer. These little signals are the unsung heroes making your tech work smoothly. Your CPU is busy chugging along, maybe rendering a video or running your favorite game. Suddenly, an interrupt signal arrives. This tells the CPU, hold up, pause that task for a sec, buddy. We've got something more pressing. Imagine you're deep into a Minecraft building session, totally focused, and then, BAM! Your mom calls you for dinner. That call is an interrupt. It makes you pause your game, save your progress, hopefully, and deal with the more urgent task. That's basically what interrupts do for your CPU, ensuring it handles critical events promptly. Without these constant, tiny interruptions managing the flow of tasks, your multi-core beast of a PC would feel more like a relic from the dark ages of computing. So yeah, interrupts? Pretty important stuff, and we're just getting started on how they work. First up in our interrupt zoo, we have hardware interrupts. These are the real-world pings, the tangible nudges. They come from actual physical devices connected to your computer. Think about it. When you press a key on your keyboard, that action generates a hardware interrupt. Your mouse? Clicking or moving it sends an interrupt. Your network card, when it snags a fresh packet of data from the internet for your cat video stream, it shouts, "Interrupt!" to the CPU. Even your hard drive or SSD will signal an interrupt when it's finished reading or writing that massive game file. These are external events demanding the CPU's attention right now. Next, we've got software interrupts. These are a bit different because they're generated by, you guessed it, software. Often, these are intentional. For example, when a program you're running needs the operating system to do something special, like opening a file, creating a new window, or allocating memory, it uses a software interrupt. This is called a system call. It's like the program politely raising its hand and saying, "Excuse me, Mr. Operating System, could you handle this for me?" Another type of software interrupt happens when things go wrong, like your program trying to divide a number by zero, a classic, or access a part of memory it's not supposed to. Then there's the concept of maskable interrupts. Think of this as the CPU having a do not disturb mode for certain types of interruptions. Most interrupts are maskable. This means the CPU can choose to temporarily ignore them if it's in the middle of something extremely critical that absolutely cannot be paused. This keeps things orderly. So, an interrupt signal has arrived. What happens next? It's not just instant chaos. There's a very specific dance, a playbook, that your CPU follows. First, the CPU doesn't just drop everything mid-calculation. That would be messy. Instead, it typically finishes the current tiny instruction it's executing. We're talking nanoseconds here, folks. Once that very specific small step is done, it acknowledges the interrupt signal. It's like saying, "Okay, I hear you. Just give me one tiny moment to put this down carefully before I turn around." This ensures the immediate work isn't corrupted. Step 2 is all about saving the scene. Before the CPU can jump off to handle the interrupt, it needs to remember exactly what it was doing and where it left off. Think of it like putting a very detailed bookmark in your code. The CPU saves the contents of its important internal storage spots, called registers, and the address of the next instruction it was supposed to execute, the program counter. This crucial information is usually pushed onto a special area in memory called the stack. This way, once the interrupt is dealt with, the CPU can return and pick up precisely where it was, as if nothing happened. The CPU needs to figure out which device or event actually triggered the interrupt. Your computer has many potential sources of interrupts: keyboard, mouse, timer, disk drives, network cards, and so on. To identify the source, systems often use an interrupt controller, which manages requests. The CPU then consults a special list, kind of like a directory, called the Interrupt Vector Table, IVT. This table contains the starting addresses of the specific routines designed to handle each type of interrupt. It's a map to the right troubleshooter. Section 4. Why interrupts rock efficiency, priorities, and juggling tasks. One of the biggest reasons interrupts totally rock is the massive efficiency boost they give your system. Remember that old slow way called polling, where the CPU constantly asks every device, "Are you there? Need anything?" How about now? That's like having a ridiculously needy friend who texts you every 5 seconds. Super annoying and a huge waste of your time and energy. Interrupts flip that script. Devices only speak up or signal the CPU when they actually attention. This frees up the CPU to do other useful work, instead of playing a constant game of "Are we there yet?" with every component. This means more processing power for your games, your apps, your everything. Then there's the awesome power of prioritization. Let's be real, not all interrupts are created equal. A signal that your battery is about to die is way more important than you just wiggling your mouse, right? Operating systems are smart about this. They implement interrupt priority levels. This means that if multiple interrupts happen at the same time, the system can decide which one is more urgent and needs to be handled first. A high-priority interrupt, like a critical hardware failure warning, can even interrupt a lower-priority ISR that's currently running. This hierarchical system ensures that the most vital tasks always get precedence, keeping your system stable and responsive. All these benefits, efficiency, prioritization, and multitasking support, add up to a fantastic user experience. Because interrupts allow your system to handle events promptly and manage resources intelligently, your computer feels snappy and responsive. Section 5, ISRs, the unsung heroes of interrupt land. So, we've talked about interrupts as signals, but what actually these signals? That's where the interrupt service routine, or ISR, steps into the spotlight. An ISR is a special, often very short and highly optimized piece of code. Think of it as a dedicated first responder or a specialist technician for a very specific type of interrupt. For every possible interrupt source, your keyboard, your system timer, your network card, there's usually a unique ISR designed to deal with exactly what that device needs. It's the code that knows precisely how to talk to that particular piece of hardware, or handle that specific software event. How do these ISRs actually work their magic? Well, when an interrupt occurs and the CPU has figured out who sent it, using that interrupt vector table we mentioned, it essentially jumps to the memory address where the corresponding ISR begins. The ISR then takes over control of the CPU temporarily. Its job is to perform the necessary actions to service the interrupt. For example, if it's a keyboard interrupt, the ISR might read the character you typed and store it in a buffer. If it's a disk interrupt, it might signal that data transfer is complete. These routines are the direct action takers. Once the ISR starts running, it typically needs to do its job as quickly and efficiently as possible. This quick in-and-out action ensures that the CPU can swiftly return to its previous task or handle any other pending interrupts. Section 6. Wrapping it up. Interrupts and ISRs. The dynamic duo. So, let's do a quick flyby of what we've covered. Interrupts are basically those super important signals that tell your CPU, "Hey, pay attention to me now." They can come from hardware, like your keyboard, or from software, like a program needing help from the OS. And the interrupt service routines, or ISRs, those are the dedicated little worker programs, the specialists that actually roll up their sleeves and the work required by each specific interrupt. They are the dynamic duo, working hand in hand to keep your computer running like a well-oiled machine, or maybe a perfectly tuned gaming rig. The importance of this duo for system efficiency cannot be overstated. Imagine your CPU constantly having to ask every single component if it needs anything. That's called polling, and it's a massive waste of cycles. Interrupts completely change that game. Devices just signal when they need something, allowing the CPU to focus on actual productive work the rest of the time. ISRs contribute by handling these requests super quickly. This efficient use of resources means your computer can do more, faster, without getting bogged down. It's all about working smarter, not just harder, for your processor. And what about responsiveness? That snappy feel when you use your computer. Thank interrupts and ISRs. When you click your mouse, type a key, or when a new network packet arrives for your online game, an interrupt fires. A swift ISR then processes that event almost instantaneously. This ensures that your actions get immediate feedback. and that time-sensitive operations, like network data or audio playback, are handled without noticeable lag.